Thank you, and good morning, all. Yeah, my name is Burak Bal. I hold an bachelor degree from Middle East Technical University and PhD from Koç University, Turkey, Istanbul. So after graduating from Koç University, I went to United States, first Purdue University as a postdoc position. Then I moved to Los Angeles, University of Los Angeles, California. For 2 years, I was a project scientist. Then I moved to Japan. For another year, I was a project leader on mostly hydrogen embrittlement. Then I moved back to I had another year at Max Planck Institute, lots of experiment and modeling. Then I moved to Abdullah Gül University. It's at the middle of Turkey, close to Cappadocia, which is the main attraction, touristic destination in Turkey. And this is my research group, and I'm doing my research with this. I have several master, PhD, postdocs, and some bachelor degree students. And my research interest is mostly on multiscale modeling, starting from atomic scale, like from picosecond, femtosecond, atomic vibrations, dispersion curves, everything to macro scale, always damage, failure, and the relationship between microstructure and macroscopic mechanical properties. And two main questions I'm trying to answer in my research is, what are the physical phenomena that control the mechanical properties, also in extreme environment conditions? And if we know this behavior, can we design more resilient materials, better materials? So today I will focus on first hydrogen embrittlement, and the outline also includes the dislocation, which dislocations we have in different crystal systems. Some strengthening mechanisms. These include solute solution strengthening, precipitation strengthening. I'll not mention grain boundary strengthening or strain hardening, but I assume you guys are familiar with these issues. So let's start with some basics in hydrogen embrittlement. So after some amount of atomic hydrogen, we see dramatic decrease in macromechanical properties. These are the macromechanical properties like the ultimate tensile strength. Sometimes we see increase in yield strength, but ductility reduced, impact strength reduced, toughness reduced, even at quasi-static strain rates and also high strain rates. We have some experiments. So hydrogen causes some problem in metals, and we have to understand what is this problem. Hydrogen changes structure mode from ductile to brittle after even 7 hours of hydrogenation. These are the same materials. The only difference is atomic hydrogen. It becomes like, we have a steel, it becomes like a glass. It's due to the just atomic hydrogen, some amount of atomic hydrogen, and it causes catastrophic failure. So I try to keep my slide at master or PhD level, so I'm sorry about the professors. This could be boring for you, but there are some ways that hydrogen can enter into the materials. I just try to summarize. So in order to talk about hydrogen embrittlement, hydrogen should be there. The first way is during manufacturing. Could be casting, could be other methods. So during solidification, the solubility of hydrogen in liquid is pretty high. During solidification, some of this hydrogen just stays there. We call it as-is hydrogen due to the casting. After some manufacturing operations like laser cutting, welding, we have more hydrogen, and during in use in environment, hydrogen can also diffuse into the materials. And once hydrogen diffuse into the material, it can be localized at trap size, or it can continue its motion, like diffusible hydrogen or trapped hydrogen. The trapped sites are grain boundaries, phase boundaries, voids, inclusions. We have several trap sites for hydrogen, and mostly the interaction of hydrogen with defects are the main controlling mechanism of hydrogen embrittlement. So diffusible hydrogen and their interactions with defects. So there are several mechanisms proposed to understand, to explain hydrogen embrittlement. I tried to summarize some of them. Hydrogen enhanced decohesion is one of them. It states that the hydrogen, while it's moving, decreases the cohesive energy between the bonding, and it causes brittle failure. Hydrogen enhanced localized decohesion. Second mechanism is hydrogen enhanced localized plasticity. We know that dislocations has some stress field, tensile stress field and compressive stress field, and interstitial hydrogen has also stress field. So according to this mechanism, hydrogen can shield the stress field of a dislocation and increase the mobility of dislocation and create some localized plastic deformation. And once that localization cannot be accommodated plastically, we have failure. So we can have some, if hydrogen over metal is greater than 0.1, hydrogen tend to become hydride at the crack tip, and it causes some blunting, and we see some adsorption induced dislocation emission. And depending on the hydrogen concentration, we can also observe the coexistence of different hydrogen embrittlement mechanisms. So the real question is, it is still unknown what hydrogen causes at molecular scale, at microscale, and the interaction of hydrogen with dislocation is the real question to uncover the micromechanism or molecular mechanism of hydrogen embrittlement. So one of the basic questions, hydrogen really decrease the dislocation mobility or increases? So this is very basic. If it's pin the dislocation or increase the velocity, it's still unknown. And when we say dislocation, we have different kinds of dislocations. I will try to explain later, but modeling is crucial at this stage in order to understand the real atomistic origin of hydrogen embrittlement. Of course, the science cannot happen without experiments, but you cannot experiment every scenario. Then we need modeling. This is multiscale modeling schema at different length scale, from picometer, femtometer to meter scale, and time scale again, picometer, nanosecond to continuum scale. So at continuum scale, we have finite element modeling, but the interaction between dislocation and hydrogen occurs at these scales. So we really, if we want to model the dislocation dynamics, we have a model called 3D dislocation dynamics. And with 3D dislocation dynamics, you can see the positions and velocity of dislocations at any given time. Below this scale, if we cannot determine our phenomenon deterministically, we have probabilistic approach like Monte Carlo, kinetic Monte Carlo, or rate or phase field theories. So these are probabilistic approach. For example, diffusion, it's more probabilistic. So we apply this theory, and also molecular dynamics at nanosecond, nanometer scale, just to catch the effect of hydrogen on dislocation mobility. So in order to really answer the question of what is the atomistic mechanism of hydrogen embrittlement, we need to perform 3D dislocation dynamic modeling, but we have two fundamental inputs for 3D dislocation dynamic modeling. One is the mobility law of the dislocation. The second one is the stress equation, effect of hydrogen on stress. And when we say dislocation, we have different dislocations in different crystal systems. Let's start with FCC. Are you guys familiar with phase center cubic, body center cubic? So which is the main dislocation in FCC? So in FCC, let me write it here. We have edge dislocation, which is just one extra half plane of dislocation. And in FCC, we have 4 different slip planes. These planes are all 1, 1, 1 plane, and 3 different direction, 1, 1, 0 direction. In total, if you do the calculation, we have 12 slip system in FCC. And let's say this is 1, 1, 1 plane, and we have the dislocation. So edge dislocation is 1/2. The plane is always 1, 1, 1. And we have 1, 1, 0 Burgers vector. Do you guys know how to determine the energy of dislocation? The dislocation energy consists of 2 main parts. The first part is elastic energy. The second part is the core energy. And if you sum them, the total energy is related with, so energy of dislocation is proportional with shear modulus GB square. So, okay, the edge dislocation is there. When we start giving some deformation to the edge dislocation, we are forming, we will check if we form or not. We have a dislocation called Shockley partials, or partial dislocation. Could be Shockley or Frank partial, but here they are 1/6, 1, 1, 1 plane, and 2, 1, 1 Burgers vector. So if we calculate GB square for this edge dislocation, so the reaction we are suggesting is 1/, we want to check if 1/2, I'm omitting the plane, 1, 1, 0 dissipates into 1 over 6, 2, 1, 1, plus 1 over 6, 2 Shockley partials, 2, 1, 1. I'll apply GB square. GB square is 1 over 4. 1 square is total 2 times 2 goes into the 1 over 36, 4, 5, 6 plus 1 over 36 times 6. So here 1 over 2 goes into 1 over 3. So this is energetically reasonable. So we always prefer to go lower energy states. So once we have edge dislocation, once we start moving, they always dissipate into 2 Shockley partials. And in between 2 Shockley partials, we have additional energy, which is stacking fault energy, right? The penalty that we pay for the formation of Shockley partials are the stacking fault energy. So in FCC always deform with edge dislocation, and once we start moving the edge dislocation, we have Shockley partials and stacking fault energy. So let's one thing keep in mind. Can you tell me any FCC material that you guys know? Like copper, like gold, like aluminum. These are very soft material, right? If you think about 100% aluminum, like a paper clip, you can easily bend them, or gold, you can easily bend them. The reason is edge dislocation. The driving force of the edge dislocation is phonon drag. Are you guys familiar with what's phonon? Phonons are the vibrations of atoms that create the phonon wave, and this phonon wave are the driving force of the edge dislocation. But these phonon waves take place at very low stresses, like 1 megapascal, 2 megapascal. You can easily activate the edge dislocation. That is why you can have plastic deformation at the early stage of deformation, right? But think about any BCC material, like tungsten. They are very hard because they deform with screw dislocation, which is thermally activated. It is not edge dislocation. So one thing to familiar with is edge dislocation. We said we have 4 1-1-1 planes. So let me put another 1-1-1 plane here. Okay. So let's say we have Shockley partials, but let's say we have another 1-1-1 plane here. All right. So this is edge dislocation. Again, for another plane, it also dissipates into two Shockley partials. Let me draw with this. So this is Shockley partial, and this is Shockley partial. So we have 2 different planes of 1-1-1 plane. Edge dislocation dissipate into Shockley partials. We have Shockley partials at 2 different planes. What happens when they meet them in the Lammer-Cottrell junction? So the reaction is now 1 over 6. The plane is 1-1-1, and the direction is 1-1-0. This is again 1-1-1, 1-1-0. These are 2 Shockley partials. Thank you. sorry, for the Shockley partial, it is 211. So it is 1/6, 211. One Shockley partial at one plane, another Shockley partial at another plane. And at this junction, we call it Lammer-Cottrell junction, we have another dislocation occurs at Lammer-Cottrell junction. It is Berger's vector is 1/6. Sorry, is it? I forgot. Maybe 1/3, 1, 1, 0. Let's check if it is energetically favorable or not. So here we have 6/38 is 1/6 plus 6/36 is another 1/8. So here we have 1/3. 1/3 goes into 1, 2, 2/3. So this is this is gonna be 6. 2/36. So 1/18. So we have an energy of 2 Shockley partial 1/3. One stay rod dislocation is 1/18. Do you think this is energetically favorable? Very much, right? This energy is very low compared to 2 Shockley partials. That is why if we have 2 Shockley partial, they meet at the Lammer-Cottrell junction, they always form stay rod dislocation. But if you try to reverse the reaction, it is impossible. You have to give a lot of energy. The penalty that you pay to create stay rod dislocation is too much. So if we have a stay rod at the Lammer-Cottrell, they just stay there. They cannot move. So it is one of the strengthening mechanism of FCC metals. So for FCC, so far you know edge dislocation, partial dislocation, sessile partial is Shockley partial. We have Frank partial, which is not glycile. Third dislocation is stay rod dislocation. So these are the main dislocations in FCC. But the main driving force, don't forget, it is phonon drag. That is why we have very early stage of deformation. And in order to, but the problem with FCC, they are soft, right? We have to increase the strength of a FCC. That is why we have solute solution strengthening. Let me draw one basic FCC curve. So saying FCC, maybe, yeah. I don't know it's the right time, but so FCC is something like this: stress versus strain. FCC, we have a lot. So this is 100% FCC. So we need to increase what we want as an ideal. Depending on the application, we want something like this. But in order to create some excess stress, we have solute solution strengthening, grain boundary, but I'll skip grain boundary. Today we can mention precipitate strengthening. For solute solution strengthening, it is proportional with GB square. We have, like, if you have a solute in the matrix, we have a size mismatch and modulus mismatch. The size mismatch is, let's call it with delta, plus modulus mismatch divided by 20 is solute solution strengthening. So in the copper edge, actually solute solution strengthening close one edge and open another edge. By the way, you cannot just arbitrarily select two elements and combine them together. We have 4 human rotary rules. First, the size mismatch shouldn't be greater than 15%. Valence should be equal. Electronegativities should be similar, and the crystal structure should be same. So back in the ages, at the silver age, let me draw this diagram. So of course, here we have square root of C. Square root of, so solid solution strengthening is proportional with square root of C. So if you draw at the copper edge, square root of C versus tau, and the slope will be this parameter, modulus mismatch, and the size mismatch divided, modulus divided by 20. So people try to add different elements to copper, aluminum, different FCCs, but once they add copper and tin, they came up with bronze, right? So solute solution strengthening close one era, which is a copper era, and open another era. It is a bronze era. So it is one of the fundamental strengthening mechanism. Yeah, another strengthening mechanism is precipitation strengthening, but I'll just stop at this point and try to define you another dislocation type, which is screw dislocation. Body center cubic materials, 100% BCC, they always deform with screw dislocation, but for screw dislocation we have energy barriers, something like this. We have energy barriers. So suppose you have a screw dislocation at this point. In order, so this is one energy landscape, this is another energy landscape. In order to move from one energy state to another energy state, the dislocation should overcome this energy barrier. It is called as thermally activated motion. We need some thermal energy in order to move screw dislocation from one energy state to another state, and it happens by part of the screw dislocation. For example, this segment, we call it kink, just moves with, so these are the edge dislocation. If you look at the Burgers vector, goes here and occur at any other energy segment. So this is called kink pair formation and propagation. Around maybe 200, 300, depending on the material, 400, 500 megapascals, you see the screw dislocation motion. That is why BCC materials are very hard materials. And if you look at the ductile to brittle transition curves, you see a distinct ductile to brittle transition temperature for BCC materials, not for FCC materials. Because FCC, let's say this is temperature versus impact energy. For BCC, it is something like this. For FCC, it is something like this. This is mainly because BCC deform with screw dislocation, which is thermally activated. They are mobile at high temperatures, but below that temperatures, they are extremely brittle. But FCC, it is athermal, just phonon drag, so we don't have any distinct ductile to brittle transition temperature for FCC materials. Anyway, I just wanted to explain some of the dislocations to you. I'm going back to hydrogen embrittlement. So here, what we need is mobility law for dislocations. And now when I say dislocation, you guys can ask which dislocation: edge dislocation, screw, Shockley partial, Frank partial, stay rod. These are all different kinds of dislocations. And yeah, for this study, we focused on edge dislocation. In order to derive the mobility law of edge dislocation, we need to perform some molecular dynamic simulations at different temperatures, with different hydrogen concentrations. Yeah, these are the main two inputs with different stresses, of course. Let me go one more slide and check. Yeah, I already explained what are the dislocations. So this is phonon drag. It's like a pendulum. The vibration of one atom also affects the vibration of another atom. They create the phonon, and we see phonon drag, edge dislocation, and boom, deformation. But for screw dislocation, we have different energy landscapes. The formation is with two edge dislocation partials. These are called king pair formation, propagation, and at the end, we have all screw formation. But one thing I forgot to say, do you think can we see cross slip in edge dislocation? Most of the textbook, it's mentioned that the cross slip is only for screw dislocation. But if we create Shockley partials, let's say we have a FCC plane. We have FCC plane, and we have edge dislocation that goes into the edge dislocation goes into two Shockley partials, and we have another 1-1-1 plane here. If two Shockley partial meets and create a screw segment, this segment also cross slips to another plane. But screw, don't forget, for FCC we said we have 4 different 1-1-1 plane. We have a Thomson tetrahedron. I will show to you what's Thomson tetrahedron so you can understand which kind of dislocation we have. In total, 12 slip system. For BCC, the Burger's vector is always 1-1-1. Do you guys know which slip planes we have for BCC? We have 1-1-0, 2-1-1, and 3-2-1. In total, 48. Even though we, including pencil glides and everything, even though we have more slip systems in BCC, FCC is way more ductile than BCC due to the fact that one is deforming with edge dislocation and another one is deforming with screw dislocation. All right, so what we have done in this research. Please look at this graph. This is for edge dislocation, literature, data without any hydrogen, just edge dislocation with different temperature and the speed of dislocation. As you can see, the lattice resistance for edge dislocation is pretty low. 10 megapascal, 3 megapascal. We have mobility of these edge dislocations, right? Since it's a phonon drag. But please check, once you increase the temperature, if the velocity of dislocation increases or decreases. Increase the temperature, check if the velocity is increase or decrease. Decrease, right? So increasing the temperature 100, 200, 300, but the velocity is decreases. This is due to phonon interactions and phonon dispersion. So these are like maybe solid state physics, but it is not always once you increase the temperature, the dislocation velocity increases. And the mobility law that is suggested for edge dislocation in the literature is tau B over B. Tau is shear stress, B is Burgers vector, B is drag coefficient. And the drag coefficient is only a function of temperature. So depending on the temperature, if you get the slope, you can find the B very easily. So this is only for 110 plane. For 112 plane, it is more complicated. And the velocity law for 112 plane, it is not a function of temperature, but just a shear stress. But we will focus both planes, but the most important equation output is here. In literature, the mobility law is only tau B over B, and the drag coefficient is only a function of temperature. What happens if we have hydrogen? If we want to study hydrogen embrittlement with 3D dislocation dynamics, we need mobility law with edge dislocation. But if we use that mobility law, it is only a function of temperature. We need the effect of hydrogen on that mobility law. That is why we had an idea. Why don't we simulate everything with MD to calculate the effect of hydrogen on both drag coefficient and also the shear stress, because the pinning stress, the critical result shear stress will also depend on hydrogen. So we performed several MD simulations. I'm sorry, let me just sit for a minute. The dimensions are very important to optimize dimension, because in order to not create image forces, you have to make your z-axis long. In order to dissipate all the heat throughout the formation and glide of dislocation, you need to make this x-axis pretty long, because we have periodic boundary conditions here. Then in order to allow kink pair formation, for 110 plane we have also kink pair, you have to adjust your y-axis accordingly. So deciding this box size was a challenging part, and the dimensions we got is 29.6 nanometer X. This axis, this is the Burgers vector line, is along Y. And 20 nanometer and 28.n. So we kept the number of atoms, millions of atoms, volume and energy constant, and we use, there is a new embedded atom potential proposed in the literature that can capture the repulsive effects of hydrogen too. So if you check the like very basic Lennard-Jones interatomic potential, you will see something like this: energy versus distance. So first you have repulsive forces. Once the atoms are very close to each other, you have a repulsive force, then attractive force, and you have the bonding distance anyway. When and et al. Also managed to capture this part, the repulsive effects of hydrogen. So we use that interatomic potential. And remember, once you get the derivative of interatomic potential with respect to any position, what you get is what? The force, right? Energy with respect to position, you'll get the force. And once you know the force, with Newtonian mechanics. So this is not quantum mechanics. These are all based on Newtonian mechanics. With the forces, you can calculate everything about this location, like the speed, like the displacement and everything. So these blue dots are the hydrogen atoms. We input them randomly. That is not the realistic approach. We have another paper, because this location is a stress field and hydrogen localized based on that stress field. So the more reasonable approach is you can place the hydrogen one by one with grand canonical Monte Carlo approach. Then once you have the hydrogen localization, you can use that configuration, input it to your MD, and run your simulation. That is another study. We also published that one in Scripta. But anyways, we had 5 different temperatures and several from 100 to 2 gigapascal stresses, almost 1.5 million iron atoms, and 4 different hydrogen concentration. Of course, these are not realistic, but in MD, you cannot put millions of iron and just 6 hydrogen there. Maybe with ab initio you can do it, but MD you have to extrapolate. All right, you have to exaggerate. Also, the strain rate limit for MD is pretty high. So we performed all the simulations for each scenario. So this took for both planes, 110 glide plane and 112 glide plane. So 110 and 112, we didn't consider 3 to 1 because it's a pencil glide anyway. But this took almost 3 years, because one run takes almost more than a week. Even in Max Planck cluster, we use Max Planck clusters, HPC, high performance UCLA, there is a also very powerful Hoffman 2 cluster, but it took us, almost 3 years. So I showed you we have several stress levels. You can define them either as a ramp function, so unit ramp, which can create some shock waves, but you can also do unit step function. From 0 to 0.5 nanoseconds, we increase the stress gradually, like slowly. And once we reach the value, we kept it steady after 0.5 nanoseconds. So basically, we are interested in this region. This is how we applied stress. And one thing that is very interesting for me is we always see a lot of oscillations of the stress around 300 megapascals. We believe that we have a resonance there. The natural frequency of the dislocation matches with the natural frequency of the system. That is the idea, but we don't know, because we also see these kind of oscillations around 600, 900. Always, once you repeat it, the oscillation increases around this stresses, then decreases and increases again. This is still unknown phenomenon for us. We need to uncover. And for 100 Kelvin, we have a 0 hydrogen with hydrogen. You run the simulations, you get the results. The dislocation moves. After 0.5, you have a displacement versus time. Once you get so these are for different temperatures. Once you get the first derivative, you can get the velocity. This is, I think, pure iron without, these are the different hydrogen, one thing that you see is hydrogen always decreases the speed of dislocation. But here, the dislocation speed is too much. So it always depends on the dislocation speed and hydrogen diffusion. If the dislocation speed is high, hydrogen always try to pin them. If they are comparable, if the hydrogen diffusion can catch the dislocation, maybe you can see the synchronized motion of dislocations and hydrogen, then you can see some increase of velocity of dislocation. So once you have these results, our idea, in the literature, it was only tau B over B as a function of temperature. Now, the new mobility law that we suggested is tau applied minus tau critical stress, which is a function of temperature and concentration, divided by Dirac coefficient, which is also a function of temperature and concentration. So, how we can get this one? We just get the first derivative and the Dirac coefficient as a function of temperature. Once you plot them, you have almost a linear line. So if Dirac coefficient as a function of temperature with different hydrogen concentration is almost a linear line, we think it's a slope times constant plus constant. But this slope and constant also depends on the legend, right? Depends on the other variables. So B Dirac coefficient is function of slope, again a function of hydrogen concentration times the temperature plus a constant, which is a function of concentration. But we don't know if it's linear, if it's parabolic. Then you get B0 as a function of hydrogen concentration, B1 as a function of hydrogen concentration, and they are also linear. So we thought B0C is B2C plus B3, B1C, B4C plus B5. So that is the B's part. And for critical stress, we also draw critical stress as a function of hydrogen concentration. Again, linear line, A0T plus A1T plus C. Once you draw A0, it is not a valid response, so we assumed it's a constant error because this is pretty low. 60 megapascal, we assumed A0 is 50 megapascal, and A1 is kind of a linear, we assumed, and A2T plus A3. Then we get all the constants, and for both dislocation planes 112 and 110, we came up with two mobility laws, which is a function of both temperature and hydrogen concentration. So if anyone wants to perform discrete dislocation dynamics and work on hydrogen embrittlement, they have to use this equation because this is the only, so it's like an interatomic potential for MD. So we have a mobility law which captures the effect of temperature, hydrogen concentration for both types of dislocations. So that is the experiment modeling part. Before going to experimental parts, is there any question? I'm so sorry if I was too boring with the modeling part because it's very theoretical and maybe it's very new stuff for you. Maybe, so whatever, I can continue and get the questions at the end too.
It's not clear what is the critical trend. Can you? Yeah. Can you go back one slide? Yeah.
Yeah, I know what you mean here. Okay, critical. You're asking about this one. Mhm. Without hydrogen, the edge dislocation moves at 1 megapascal, 2 megapascal. The lattice resistance is very low. Whatever you apply, you get the dislocation motion easily. But with hydrogen, suppose you apply 100 megapascal, but hydrogens goes to the core of the dislocation and pins the dislocation there. They cannot get away from the hydrogen at the early stages of deformation. The stress that get away from the hydrogen deepening stress is the critical stress in this equation. Suppose you apply 100 megapascal, but hydrogen released from the dislocation at 50 megapascal. Applied is 100, but the critical is 50. So it's like a critical Zorch stress.
I was thinking about the phonons because you said you can simplify your potential going only to model forces, but then where the phonons get into your model, or aren't they useful in your model?
That is very, very good question, but we are currently working on microscale, microsecond or nanoscale with MD. In MD cannot capture the effect of phonons. So that I understand, of course, phonons are very important. We can capture the mechanics of phonons and the kinetics of phonons, maybe even the very low temperature phonon statics or dispersion curves, I don't know, but we cannot do it with MD because it's very Newtonian mechanics. We are solving the Newtonian mechanics with MD. Maybe using ab initio or lower scale modeling. I know only ab initio. I don't know any other modeling tool for like DFD. It is another research topic. It's another research that will definitely affect the behavior and the interaction of phonons, maybe also affect the dislocation behavior too. Maybe, but maybe, yeah. Of course, these are like continuum models, but if we try to include some implicit variables, we always have like several others. If you deepen your scale, you always find something new. Yeah.
Thank you for the very nice talk. We can reduce the system for a stress, elastic stress, where the velocity is equal to 0.
Yeah. Or this is what you are talking about, I guess. Here, the stress is pretty low, right? The velocity is almost 0. And after 1, 2, 3 megapascal, we see edge dislocation motion. But if you look at screw, you need maybe 100, 200. Screw is very different. But with hydrogen, we don't see any think before 50 megapascal. But yeah, at very low scales, you can always, do very, very small deformation and observe the dislocation velocity. Mhm. Yeah, Professor.
Any other questions? I would like to make my question too. The other slide that you presented regarding the increase in the stress with the hydrogen concentration, and you showed that the stress is more steep with an increase in temperature. I think it's no no, this one, the middle, at the middle of the slide. And I yeah, the critical stress. And I trying to rationalize on a, let's say, test wise, what we've seen during the test is maybe I lost in the explanation, but it is maybe due to the fact that hydrogen diffuses at the, let's say, I'm thinking about much more like this continuous yielding or the serration light effect that you have, that the running between the dislocation and hydrogen, in order to want the dislocation traps the hydrogen traps the dislocation, and then you have a new cycle of releasing or creating new dislocation. It's pretty much like that. To be very specific on the question, I didn't get how the critical stress increases with temperature. It's mobility wise related regarding the hydrogen pinning dislocations. If you look at the lower temperature, like 50 or 100 kelvins, you have a less TP curve. And then for 200, 300, 400, so on, the increase it's greater than for lower temperatures. I'm trying to rationalize regarding the mobility, because when you look at this continuous yielding or serrations in curve that you see, it's pretty much like that. The competition against the dislocation mobility and the species diffusion.
Yeah, that's very good question. The question is, okay, we understand as the hydrogen concentration increases, the critical stress increases, but why, as the temperature increases, the critical stress also increases? Of course, we have another point here, decrease, but I think, so these are like with experiments, we have very low hydrogen and we can see deepening and also synchronized action. But here we only see pinning of hydrogen. And as the temperature increases, maybe because you do relaxation before going to the simulation, right? You're putting hydrogen at the global minimums, but at 100 Kelvin, the region away from the dislocation source could be like here. The maybe local minimums are more here, but as the temperature increases, more hydrogen goes to the core of the dislocation, because that is their minimum energy landscape, and they pin more, and we need more stress to overcome. That is why the critical stress could increase. But we have to check if my answer is correct or not. This could be one explanation. Yeah, that's what I think right now. Any other question? Yeah, please.
Is this 2D analysis? 3D? So you are considering the line of the dislocation with different concentrations of hydrogen atoms in this line?
Correct. So you put all random hydrogen, we
So this concentration of hydrogen is also being considered in these lines. Okay. Yeah. Okay.
Uh, I know this group, Professor Leonardo's group, is also working on superalloys. That is why I'm sure you guys know better than me, but I wanted to show. So some slides I just passed through very quickly. For FCC, what I want you to show is so these are Shockley partials. This is Stekenfold energy. So these are some TEMs of Shockley partials. In between them, we have Stekenfold energy. Yeah, cross slip. Once two Shockley partial meet and form this, we can see also cross slip of edge dislocation. But I wanted to show you the Thomson tetrahedron. So this is the Thomson tetrahedron. Each face, we have 4 faces, is 1, 1, 1 plane. We have ladders. Let me show you the total ladders. So this is the total representation of Thomson tetrahedron. So the corners are A, B, C, D. Midpoints, we have D, C, A, B, and the centers are beta, alpha. And the perfect dislocation in magnitude from edges of the tetrahedron AB, BC. So from AB to BC, we have perfect dislocation, 1, 1, 0. If you want to see Shockley partials, you want to see the corner to the center, A to beta or B to alpha. So this Thomson tetrahedron will show you from center to center. We have another dislocation type like Frank partial or stay rods. So these are Frank partials and Lumber-Cuttle junction stay rods. Yeah, the energy is very low. You cannot overcome that. So this is FCC for BCC. As we mentioned, we have 48, and screw dislocation motion is with kink pair formation and nucleation, and the mobility law for screw dislocation is with actuation energy. We talked about solute solution strengthening. There are 2 effects that activates that affects the solute solution strengthening. One is size effect and the other one is modulus effect, modulus mismatch and size mismatch. And in total, it is a total solute solution strengthening GB square, square root of C, I think I wrote it before, size mismatch plus 1 over 20 modulus mismatch 3 by 2. This is solute solution hardening, but for nickel superalloys, the precipitation hardening is the main strengthening mechanism. But here we have several types of precipitates, and the degree of strengthening depend on the particle size, particle volume fraction, particle shape, structure of particle, natural interface between the particle and the matrix. but we have more mismatches and also several different mechanisms. Let me go very quickly and show this slide to you. If the particle size is low, we have coherent particles. We can cut through the particles, and as the size of the particle increases, we get benefit from strength. But so this depends on the aging time. After a certain point, you have bigger particles, bigger precipitates, but you lose coherency, so you have overaged incoherent particles. They are not good for us. So for metallurgists, you need to find the critical aging time and the critical size of a particle. So the first mechanism is called Friedel cutting. You can cut the particles. The second mechanism is called Oravan looping. You start some looping around the particles. So this is the TM of Friedel cutting and Oravan looping. So these are the particle types. You can have coherent, all crystal planes lined up, semi-coherent. Again, we have some lined up crystal planes. Incoherent, but we have two kinds of incoherent. Different crystal orientation, different crystal structure. Incoherent could be two different kinds. But once we have a precipitate and matrix, we have 6 different kinds of mismatches. Let me go. We have a coherency strain, but this is function of modulus mismatch. The formula is here. The second mismatch is chemical mismatch, which is not very, very dominant, but we have also chemical strengthening between metal and precipitate. We have Steffen-Fold energies, antiphase boundaries. Again, antiphase boundaries, like gamma prime phase. Ordered for low antiphase boundaries, early stage of precipitation, late stage of precipitation. But at the end of the day, the Oravan is very simple. The equation is here. At the end of the day, the equation that you use for deforming particles is this guy right here. If you go ahead and check, C depends on the specific mechanism of hardening, and epsilon relate to hardening mechanism. And for Oravan looping, GB over just L prime, the spacing between the particles. For superalloys, I just wanna show, of course you guys know better than I do, but we have ordered and disordered intermetallics. We have, like, suppose you are working with gamma prime phase. For one atomic displacement, for FCC, you lined up all the atomic arrangement. But for gamma prime, like this phase, once you go for one atomic step, you create some disorders. So these are antiphases. In order to return back to original position, you need 2 atomic steps. And now, before, H dislocation was 1/2, 111, 110, but for nickel-based superalloys, for gamma prime phase, we have super dislocation. It's called a super dislocation. It is not 1/2, but instead 1. So we have super dislocation, causes not Shockley partials, but super partials. And in between super partials, we have antiphase boundaries. Also, let me go very quickly. Here, we have super partials. In between super partials, we have imperfect zone with nickels and aluminiums. They are not lined up. It is antiphase boundary. Of course, this superpartial will also dissociate into Shockley partials. Let me show you. So this is L1, 2 dislocation, perfect dislocation, 2 superpartials. In between them, we have antiphase boundaries. Yeah, and also this superpartial will dissociate into Shockley partials and intrinsic stacking faults. So we have two superpartials, so they will go into this reaction. The total reaction of the super dislocation goes into the Shockley partial plus complex stacking fault, Shockley partial, antiphase boundary. You see, stacking fault is 1.5 nanometer, antiphase boundary is too much. This is one of the main reasons why we have very good properties even at elevated temperature. This is the deformation, like dislocation movement. Again, Shockley partial, intrinsic stacking fault, and Shockley partial. This is the scenario in superalloys. So I'll not go into Kerr-Wilsdorf lux, but I want to continue my presentation very, very quick. I don't want to bother you for the experimental part because you guys are very good facilities. I just wanted to show you what we have done with experiments. So we had so this is during my group leader at Kyushu University. We had a high pressure hydrogen charging. We got EBSD. So I just wanted to show you which capabilities we have with experimental. We did TDS analysis, measured the diffusible hydrogen concentration. We had a in situ tensile test. And so this is just a representation. We got the tensile test with different strain rates and observed that we see much more embrittlement at lower strain rates. So for higher strain rate, green and red, maybe 10% ductility loss, but here we have 45% ductility loss. And we try to work hardening rate to reach the plastic stability or not. We did some SEM fracture surface analysis. We see both show ductile fracture. So we have SEM, the fracture mode changed from ductile to quasi-cleavage. These are the EBSD after 30% of deformation. We saw some nano-twins, two different twin systems without hydrogen and with hydrogen. So hydrogen increased the microstructural features. We measured the dislocation density, the average twin thickness. Of course, if it's lower, much more hardening. So here we have 30% deformation in situ SU. So we did the tensile test inside the SEM chamber in situ. So these are the slip bands at 30% of deformation with and without dislocation. Again, we measured the dislocation density. So with 14% deformation, we see some marks with hydrogen where we don't see anything there. So hydrogen increased the maybe localized plasticity. Again, 20% hydrogen increased the microstructural features, more defects, more lines, slip lines we have with hydrogen. 25% deformation, same. So for TWIP steel, we didn't have any hydrogen embrittlement mechanism, but we proposed the mechanism. We have firstly primary twin boundary, then nanotwin distorts the boundaries, and hydrogen slip line distorts the boundaries. Hydrogen localized there. We have additional nanotwin. Hydrogen always decrease the nanotwin size, but increase the microstructural features. Then we have a lot of stress here. And crack propagates. Crack, this is twin boundary cracking, the mechanism due to hydrogen that we proposed to the literature. Of course, for low strain rate, you provide much more time to dislocation hydrogen interactions anyway. That is why you can see more embrittlement. But with ballistic tests, impact tests, Split-Hopkinson test with and without hydrogen, we also saw some embrittlement. Yeah, that's all I have for today for you guys. I'm sorry if I was too boring with lectures and everything, but thank you all.
Thank you. Any other question regarding the practical part? I should say that my former students of mechanical behavior of materials, lots of things that he presented, I should say, I said it to you. I showed to you. All that stuff regarding slip systems and FCC and so on. So it was a good match. And all of the stuff regarding hydrogen embrittlement to the ones usual that conduct studies at mechanical properties and so on. It's a very important part of what we do here regarding oil industries, nuclear application, and so on. So anyway, this is just the beginning part of fruitful collaboration that we're going to have. So we'd like to thank you once more. Thank everybody that came. We're going to record the presentation, so the ones that couldn't be here will also have the chance to see. Yep. Oh, okay.